Welcome! In this video I will introduce you to stiff systems. You will see two examples of what stiff systems are. And stiff systems are important to recognize as you will encounter difficulties when you're trying to solve them numerically. Let's start with the first example. You see a first-order linear differential equations with a solution y of t below. You see that the solution contains cosine, sine and exponential terms. This solution is plotted in green on the right. This is an interesting graph. We see that in the beginning of the solution rapidly increases and then starts oscillating. If we zoom into the very first part of the green graph, so when t is still very small, we are in the rapidly increasing part of the solution. If t is close to 0, then the cosine is almost equal to 1 and the sine to 0. So the solution will behave as the graph f of t, plotted in orange. It is clearly visible that the graph of the exact solution y of t is very similar to the graph of f of t. Now we will take a closer look at the rest of the graph, from a small t until t up to 6 pi. We see that the exponential terms vanishes as t increases, such that the graph starts behaving like the remaining cosine and sine parts. On the slide you see the exact solution y of t and the graph of g of t without the exponential term. It is clear that these graphs are also very similar. We see here both images that show the just encountered behavior in the beginning of the solution and later on. We see that the solution contains two parts, a rapidly increasing part or rapidly stabilizing. This is called the transient. The second part is oscillating, also called slowly varying. We will show you a second example. We see here a system of linear differential equations with the necessary initial conditions and its exact solution y of t. The two components y1 of t and y2 of t are shown in the orange and red graphs in the image on the right. This system contains two eigenvalues, namely -2 and -2000. The enormous difference between these two eigenvalues determine the behavior of the solution. Like the previous example, we see in the beginning that the solution is rapidly increasing and then slowly fading. We see this behavior again in close-up. First, we see the beginning of the graph for t is very small, and then the exponent of -2 times t is approximately equal to 1. The solution behaves then as is shown in the brown dotted graphs f1 and f2 of t. As is clearly visible in the graph, the exact solution and the approximated solution are very similar. This image shows the second part of the solution. When t gets bigger, the exponent of -2000t is almost equal to 0, so the solution will behave, for t getting larger, as g1 and g2 of t, shown in the yellow dotted graphs. Here we see as well that the exact and approximation of the solution are similar. Again, the beginning and the rest of the exact solution shown next to each other. We see similar behavior as in the first example. We see a rapidly increasing or stabilizing part, and the second part is slowly varying. There's a huge discrepancy in the behavior in the beginning and the rest of the solution. And we've given this behavior a name. So when the solution of an initial value problem has a rapidly stabilizing and a slowly varying part, we say that the rapidly varying part is the transient of the system, and we call this system a stiff system. Now you know how to recognize the behavior of stiff systems. Such systems will lead to difficulties when you want to solve them numerically. In class you will learn how to deal with these numerical difficulties.